Chapter 4, we're going to look at the generic graphs of sine and cosine. And as we move further in, we'll learn how to change what these graphs looks like with their amplitude, period length, and their phase shift. So up here on the screen, we have a graph or a picture of what we call a generic curve of the sine curve. Noting that our graph starts here at 0. It goes up to a high of 1 on the y-axis and down to a low of -1 on the y-axis. We've talked about that before, but y has values that fall between, or sine has values that fall between 1 and -1. That's illustrated here on the graph. Now again, this is one period of the graph. This continues on in both directions, so this graph would continue on in this direction back here, and would continue on this way. This again is just one period, which means that it's our generic period, or the one closest to the y-axis, the one that critical points that we work around. So I just mentioned the phrase critical points. The graph starts here at 0. It has a quarter point at pi/2. The quarter point is also called the first maximum. You can see maximum because it's the highest point on the graph right here. We have a midpoint at pi. We have a 3/4 point at pi/3pi/2, and that's also referred to as the first minimum. You can see it's the lowest point in the graph, and our first generic period ends at 2 pi. So 0, pi/2, pi, 3pi/2, and 2 pi are called critical points. We will refer back and forth to those quite a bit moving forward as we go through the graphing process. So one more time. It's written down here in ordered pair format, I believe. Starts at 0. When I say it starts at 0, I'm talking about the x-axis, so 0, 0. Quarter points at pi/2. The y-coordinate's at 1. That's the first maximum. Has a midpoint at pi and 0, so it crosses back to the x-axis again. 3/4 point at 3pi/2 on the x-axis, and -1, and the end of one period is at 2 pi. As I mentioned and showed on the graph already, sine is a periodic function. Means it repeats itself over and over again. The domain goes on forever, from negative infinity to positive infinity. It just repeats itself every 2 pi radians, which will bring us to a period length formula that we'll talk about later on as well. Period length equals 2 pi divided by b. But again, that's a look at the shape of the sine curve, and also listing out those generic critical points that we'll refer to back and forth here very shortly. Sine or cosine curve looks a little similar. At least it has the same 5 critical points. Our graph starts here at 0, but it starts up here at 0 and a +1. I guess before we get to the critical points, I'll note that it goes up to 1 and down to -1 on the y-axis as well. We said sine and cosine all fall between 0 and 1, or 0 and -1. Back to our critical point, starts at 0, starts up high, comes down to the x-axis at our first critical point at pi/2. It has a midpoint at pi. That midpoint is the first minimum. Again, you can see that's the lowest point on the graph. A 3/4 point at 3pi/2, and an end point, or end of one generic period, at 2 pi. Much like our sine curve, our cosine curve continues on forever in both directions, from -infinity to positive infinity. This is just the one generic curve that we refer to. It's on the positive side of the y-axis. So these are our smallest set of values to work with and to compare all of their graphs to. Listing down here are critical points in ordered pair format. It starts at 0 and 1. That is our highest point on the graph, or our first maximum. Quarter point at pi/2 and pi. It comes down to the x-axis. Midpoint at pi and -1. That's our first minimum. 3/4 point, 3pi/2 and 0, and the end at 2 pi and 1. As we progress here, we have some variables that can change what that graph looks like. A is referred to as the amplitude. It's how high and low the graph goes on the y-axis. So if our amplitude was 2, this graph would go up to 2 and down to -2 on the y-axis. The amplitude is going to change how high and low those critical points go on the y-axis. A negative amplitude creates a reflection of the graph. So if the original sine curve looks like this, then the negative cosine curve looks like this. It's just a reflection. Goes the opposite direction, and we'll cover that here shortly. B determines the period length. I already put that formula up here once. We'll highlight it here yet again. Period length equals 2 pi divided by b. From our equation, you can see b is the value in front of the x, the coefficient of the x term inside our parentheses. Our domain goes from negative infinity to positive infinity. It means it continues on forever. We're just going to graph a certain number of periods of these. Our critical values, as we go to graph new information, is found by setting the argument, in this case bx plus c, whatever is in parentheses is referred to as the argument, equal to what corresponding critical points we need to find. Typically our starting point, our quarter point, our midpoint. We solve for x and we use those values to plot. We will look at the c value in a subsequent lesson, so today we're just looking at a and b. And we're going to start right in by graphing here. Find the starting, quarter, mid, 3/4, and end points for the function y equals 1/3 x, and then we'll graph 2 periods. So our starting point here, or where we begin our process, is we take that argument, which is 1/3 x, and we set it equal to whatever critical points we want to find. In this case, I want to find the starting point. So I'm going to backtrack a couple pages here to our sine curve. Notice our sine curve starts at 0 on the x-axis, so that's what I want to set my argument equal to, is 0. Now the good news for today, when I multiply both sides by 3 to solve for x is going to equal 0. My starting point is going to stay the same. It's going to be 0. Kind of a sloppy 0, so let's try that again. X equals 0 is our starting point. We're going to go through the process another time or two. 1/3 x equals, I'm going to backtrack again. Now I want to find my quarter point, or my next critical point, moving from left to right. So back here you can see the next critical point is at pi over 2, which means that's what I want to set my argument equal to here, is pi over 2. I'm going to go ahead and solve this equation for x. I'm going to multiply both sides by 3. 3's cancel, and we have x equal to 3 pi over 2 for our quarter point. I'm going to continue that process on. We'll find our midpoint next. Starts the same way. We take our argument, which again is at 1/3 x. I'm going to backtrack again. Notice our midpoint is at pi. So we'll set this argument equal to pi. Multiply both sides by 3. And x equals 3 pi is our midpoint. We'll keep pushing on here and get all 5 critical points. 1/3 x equals our 3/4 point. You can see occurs at 3 pi over 2. So I set my argument equal to that 3 pi divided by 2. I'll multiply both sides by 3, and our 3/4 point is at 9 pi divided by 2. That's our 3/4 point. And one more time here to get our first 5 critical points. 1/3 x. Argument set equal, we want to find the end point, and the end for sine occurs at 2 pi. So we'll set our argument equal to 2 pi here. Multiply both sides by 3, and x will equal 6 pi will be our end point for the first generic period. Okay, so there's our starting process. We're going to find critical points based on that generic curve that we introduced at the start today. So what I'm going to do here is I'm going to label these critical points in order: 0, 3 pi over 2, 3 pi, 9 pi over 2, and 6 pi. It's probably not easy to see in this format, but what I'm going to do is change these, and I'm going to put this over 1. It's a visual representation here, and I'm going to write all these next 4 terms with a common denominator of 2. So the 3 pi over 2 isn't going to stay, it's going to change. 3 pi over 1, if I multiply both by 2, I'm going to have 6 pi over 2. Makes sense that 6 divided by 2 is 3. We'll leave the 9 pi over 2, and then we have 6 pi over 1, so if I multiply that by 2, I'll have 12 pi over 2. So what you'll notice here, or should notice, is these critical points are all the same distance apart. In this case, we're adding 3 to our numerator. Since I'm going to graph 2 periods, that means I need to have 4 more critical points. I'm just going to label those down here by adding 3 to my numerator: 15 pi over 2, 18 pi over 2, 21 pi over 2. I got to slide down here to get 24 pi over 2. So when I graph 2 periods, I need a total of 9 critical points. The end of one period is the beginning of the next one. Okay, so that's how we come up with our critical points. We find, based on say our argument equal to those, then we can find those incremental values and then use those to graph. Notice that we have to graph 2 periods. I want to sketch my x and the y-axis. I need to backtrack or back up here a little bit. Y equals 2 times the sine of that, so that means my amplitude is 2. What that tells me on the y-axis, I go up 2, 2, and down to -2. I'll label those on the y-axis. Then I'll label my critical points, hopefully trying to put those about the same distance apart. 3 pi over 2. Also noting when I put these down here, I don't use the unsimplified fraction, I use the simplified version. So 6 pi over 2 is 3 pi, 9 pi over 2, 12 pi over 2 simplifies to be 6 pi, 15 pi over 2 doesn't simplify, 18 pi over 2 is 9 pi, 21 pi over 2, and finally 24 pi over 2 is 12 pi. And then the final piece of this is we plot essentially those critical points. This is a sine curve, so sine curve starts down here at 0. Our first critical point is a quarter point, also the first maximum. The next point comes back down to the x-axis. Our 3/4 point is the lowest point on the curve, the first minimum. And our 5th point here is our end point. It comes back to the x-axis. And then we can just follow that pattern as we move through all of our critical points. And we sketch our curve to go through each of those critical points. And you can see we have 2 periods, starting here, ending here, ending here. We have 2 periods of the sine curve drawn there. Okay, so we'll try the next one. What's next? Same thing, graph 2 periods of y equals cosine. Oops, not quite, I guess we're not there yet. We have to find the period length of each of the following. So I wrote this equation up here, and it was in our notes. Period length equals 2 pi divided by b. I'm also going to put up here y equals a times the cosine or the sine of bx plus c. So hopefully it's a little bit easier to identify a, b, and c. So right here, a is our amplitude, 2, 3, and 4. That does not come into play on the period length. This number, 3/4, 1/2, and 3, those are our b values. So to find our period length, we do 2 pi divided by b. In this case, we just said b was 3/4. We should all know by now when we divide by a fraction, we multiply by the reciprocal. So I multiply by, not pi, just 4/3. So let's get rid of that pi out of there, just to avoid any confusion. And when I multiply that, my period length is 8 pi divided by 3. Fairly simple process as long as we can identify b out of there. We'll go ahead and move on here. Again, period length is 2 pi divided by b. Looking at this equation, our b is 1/2. Showing that 2 pi times reciprocal is 2 over 1. So our period length here is 4 pi. And one last time, period length 2 pi divided by b. In this case, b is 3. There's no fraction to simplify, so here our period length is 2 pi over 3. And you'll see that equation quite a bit moving forward. That's how we find our period length, 2 pi divided by b. Now we'll get back to some graphing. Y equals 2 times the cosine of 3x. I'll note that our amplitude is 2. We'll come back to that as we get to our graphing part of that. But we'll start out by taking our argument, which is 3x. And let's go back a couple pages here. Cosine starts at 0 on the x-axis. So we set this equal to 0. What you'll find, or I hope you've noticed already, is that cosine and sine have the same 5 critical points on the x-axis: 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're going to zip through our next critical point, 3x. As I just mentioned, our quarter point on the x-axis is pi over 2. I'll divide by 3. Dividing by 3 is the same thing as multiplying by a third. So my quarter point is at pi over 6. And continuing on, our next critical point off of that generic curve is at pi. Divide by 3, and x equals pi over 3 for my midpoint. I'm going to stop there because we've already established that these three critical points should be the same distance apart. So up here, I'm going to rewrite those with a common denominator. Looks like between 1, 6, and 3, my common denominator is 6, so I'll leave the pi over 6, but I'll change pi over 3 to be 2 pi over 3. And once we see this, we should be able to see that our spacing is the same, and that would allow us to find our next several critical points just by finding that incremental value. I need to change that to a 6, my bad. So 2 times pi over 3 was 2 pi over 6. So we go 0, 1, 2, which means my midpoint, or my three-quarter point is at 3 pi over 6, end point at 4 pi over 6. We're graphing 2 periods, so I need more critical points. I'll just keep going. 5 pi over 6, 6 pi over 6, 7 pi over 6, and 8 pi over 6. So those are the critical points that we need in order to be able to graph this particular function. I'll go ahead and try and put those on our coordinate plane. Again, bringing our amplitude back into play, we're up to 2 and down to -2. That's from this lead coefficient here. And then we have 0, pi over 6. Noting when I put these in here, they are in simplified form. So 2 pi over 6 is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6. 6 pi over 6 is just pi. 7 pi over 6. And finally 8 pi over 6, which is 4 pi over 3. Now we're ready to plot points. Cosine starts up high. So I start up here. First critical point or quarter point comes down to the x-axis. Next one has a first minimum at the midpoint, back up and back up high. There's our first period, and we just continue that pattern to graph our next period as well. And it goes down, comes back up, goes down, and finishes back up here. So there is 2 sketched in periods of our cosine curve. So you've seen both the sine and the cosine curve here in our first 2 examples of graphing. We'll go ahead and graph 1 or 2 more here to polish off this section. It says to graph 2 periods of y equals sine times the pi of x. Nothing has changed here except our argument looks a little bit different. Pi times x is our argument. Our starting point's at 0. We'll divide by pi to solve for x, and x will equal 0. Yeah, 0 divided by anything is going to be 0. So there's our starting point. To find our quarter point, we'll take that same argument of pi times x and set it equal to our quarter point on the generic curve, pi over 2. Divide by pi is the same thing as multiply by 1 over pi. Hopefully you notice here that the pi's cancel, and our quarter point is at just 1/2. There's no pi involved in this one. We'll go again here, get our critical point for the midpoint. Pi times x equals pi. I divide by pi, and x equals 1. Pi divided by pi is 1. There's our midpoint. So just like I've talked about already, our critical points are going to be spaced out the same distance. This one I hope we all can see. If we go 0, 1/2, and 1, we have 1.5, which is 3/2. 2, we're going 2 periods, so I'll keep going. 5/2, 3, 7/2, and 4. So those are our points along the x-axis. Notice we don't have a number written in here, so we should always know there's a lead coefficient of 1, so my amplitude is up to 1 and down to -1. We have 1/2. Let's try that again. That's kind of bad. We have 1/2, 1, 3/2, 2, 5 halves, 3, 7 halves, and 4 will get us our 2 periods. We're graphing sine here. Sine starts down here, moves up, comes back down, hits the minimum, ends here, and it just continues on in that pattern. We said on numerous occasions a periodic function. It just repeats itself over and over again. What we're doing here is graphing the first 2 periods, moving from left to right, and we'll end up right there. So there's our sketch of 2 periods of y equals sine of pi times x. Notice the pi has just disappeared from our x-axis. And that should be, no, we have one more. Y equals -2 times the cosine of 4x. We'll come back to this negative amplitude, but we have an amplitude of -2, which obviously gives an amplitude of 2, but also going to change to that reflection. We'll start out here by finding our critical points. 4x is our argument, set it equal to 0, divide by 4, x still equals 0 is our starting point. So as I mentioned already once or twice, all of our starting points today will be at 0. Our next critical point for cosine occurs at pi over 2. We'll divide by 4, which is multiplying by 1/4, so x equals pi over 8 is my quarter point. And one more critical point so we can find or verify our incremental distances equals pi divided by 4, and x equals pi over 4 for our midpoint. If we put those in order over here, 0, pi over 8, I'm going to write them all the same common denominator, so 0 over 8 I really don't need to rewrite, but pi over 4 I will rewrite as 2 pi over 8. And from here it should be easy to see we add 1, so our next critical point is at 3 pi over 8, and we'll just fill all of those in. 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and 8 pi over 8 will get us our 2 period lengths with those 9 critical points. So here, I mentioned our amplitude was -2, but we still go up to 2 and down to -2. And we'll put those critical points on here. Pi over 8, 2 pi over 8 is pi over 4, 3 pi over 8, 4 pi over 8 is pi over 2, 5 pi over 8, 6 pi over 8 simplifies to be 3 pi over 4, 7 pi over 8, and 8 pi over 8 simplifies just to be pi. Now here's where the amplitude makes a difference, or the negative amplitude. Cosine would typically start right up here, but because we have a negative amplitude, it's reflection, so it's going to start down here and then move its way in the opposite direction to where we go across the x-axis, up high, back down, and to here, and we just follow the same pattern all the way through to graph our 2 periods, connecting all of those critical points that I keep pushing the wrong button on. But we'll finish our graph right here, and there's 2 periods of our sine or cosine curve with a negative amplitude. Once again, pointing out it's a reflection of the original graph. And that covers our first section.